Okay, today we will start by going over the assignment 3. This is preparation for the quiz or the exam. I should call them exams. The exam on Monday, right? We have an exam on Monday, or quiz on Monday.
Is there a practice quiz online?
Yeah, there is a practice quiz up there. There's quiz 3. And I already posted the answers, but I want to highly recommend that you do not look at the answers until you're really made a big effort to solve the problem. And making a big effort to solve the problem includes actually coding your solution and running tests on it. That would be excellent training and practice for you to go through if you have the time to do that. All right. Now on the quiz, we just write down our code solutions without the use of a computer. So we need to practice that at least. And so let's look at the first one. It's a function R identical. Are two vectors A and B identical? I had trouble copying and pasting from this before, didn't I? Let me, I guess I'll just do it. So two functions are identical. Sorry, a function are identical, two vectors. So your solution can look like this. You don't need to copy the function declaration, the function signature. You don't need to copy that. But you could if you want. It may help your thinking, but it's not necessary. So you could do this. If A dot size is not B dot size, then return. And if the two vectors have different sizes, then they're not identical. So we want to check that first, because we're going to do pairwise comparison. The first element of A will compare to the first element of B. Second element of A will compare to the second element of B. Now that loop that we have to write to do that pairwise comparison, that loop will not work correctly if they have different sizes. So the first thing we do as preparation for that loop is to check to see that they have the same size. If they don't, return. We want to return, it's a Boolean value. We're supposed to return true or false, whether they are identical or not identical. In this case, we return false, they are not identical. Now we're going to do a pairwise comparison. We need to compare A of I with B of I. Did I do this problem yet? I did this, didn't I, last time? Now this is the natural thing that people think, when they start the problem. And we're going to have to modify that. This is not the way to go, right? But I'm writing it like this because it's the natural way that I have noticed people think about the problem. I don't know if I think about it that way. Maybe I do as well. Well, I just quickly adjust my thinking as I realize I need to go the other way. And I'm being vague about that now, but I'm going to show you what I mean. We need to do pairwise comparison. Every element of A has to equal every element of B. So I is less than A dot size. Now we could do less than B dot size. We know that they're identical. They're the same size. There's our loop. Now we want every element to be the same. So this is the first step, right? But this fails. Because if A of 0 equals A of B, they're true, and we return true. We don't even look at A of 1. Why should we just looked at the first pair of elements, and we concluded prematurely that the two vectors are the same. So this logic will not work. The return true must be done at the end of the loop, after we've looked at every element and failed to find two elements that were different. If we find an I, such that A of I is not A of B, we know right there on the spot that A and B are not identical, because we found one example, one instance where they are different. But if we pass through this loop, which looks at every possible I, and we didn't return false, then we know that we've looked at everything and we're good. So we return true. All right, I think we covered that last time, but maybe not. Is unlucky. Implement a function that determines if the unlucky number 13 appears in a vector. The function returns true if 13 appears in the vector at least once. Otherwise, it returns false. Well, that means we need to scan through the vector and look for 13. If we find it, we return false. If we don't find it, we return, if we find it, we return true. If we don't find it, we return false. So it looks very similar to the problem we just solved. We scan through the vector. I think it's V in this case. And if V equals 13, we know on the spot it's unlucky. So we have to return true. Because the name of the function is unlucky. We want to know, is it unlucky? We only need to find 113. So it's a little bit different from the previous problem. After we scan through the whole vector and we don't find a 13, then we can return false. It is not unlucky. Write test code that tests every statement in the isUnlucky function you implemented in the previous problem. Express your tests using assertions that tests every statement. How many calls to isUnlucky are needed to test every statement? Actually, this is an entire statement unto itself. And the thing is, we want to hit this, and we want to hit this. This is a substatement. This is a statement within this parent statement called an if statement. So I want to make sure that we execute this return value and this return. So we need to construct a vector. Let's put a number on it. Although we could actually test it right here. I'll give you a minimal test that works. But it's not a great test. This is assert is unlucky. B is empty, but the function should still work. See, an empty vector is not unlucky, according to our definition of unlucky. If we push a 4, it's still not unlucky. But if we push to 13, now v has 13 in it. The function should return true when we pass it to is unlucky. I'm just speeding through these, and let me know if you have a question about this. You can stop me if you like. Is strictly increasing. Write a predicate function. Oh, what's a predicate function? What is that? Who knows what a predicate function is? What's the definition of a predicate function? It's actually very simple. It's a function that returns true or false. That's it. So it's like it's a terminology that comes from logic, study of logic. So we call it a predicate. It's a statement that's true or false. And an expression that evaluates a true or false. Write a predicate function called is strictly increasing that checks whether a vector of integers contains values that are in strictly increasing order. A declaration of the function is shown in figure 3. The function returns true if the elements are in strictly increasing order. Otherwise, it returns false. Here's an example. Let's do this. So we have vector v. Here it is strictly increasing. We want to test that v, the values in v, get bigger as we move through the elements in v. So obviously we need a loop. It's just like the other ones. If we find a bad pair, we're going to compare each element with its successor. And if we find a bad pair, we'll return false. If we don't find a bad pair, then we know we can return true. What does it mean to find a bad pair? Well, if v of I is bigger than or equal to v of I plus 1, that means something is bigger than or equal to its successor. Then we know that it's not strictly increasing, so we'll return false. Now there's a mistake here. This is not full credit answer. What is the mistake? Yeah.
For your for loop, you have to subtract 1 from v size.
That's right. Good. We're going too far because we hit the last element, but the last element has no successor. So we can't stop. We can't go to the last element. We don't have to worry about the last element. It has no successor. So we want to stop at the element before the last element. Because this, v of I, once we hit v size minus 2, that's the last valid index, or that's the last index we care about, then we're going to compare that last item, the second to last item, with the last item. So the last item is still looked at, but it's only looked at once. It's not looked at twice. There we go. All right, let's do 5. Is there a 5? No, there it is. Flatten. Write a function named flatten that takes a 2-dimensional array of integers with 100 rows and 200 columns and returns a vector that contains all of the array array's elements. Copy the values a row at a time. In other words, copy row 0 into the vector, then row 1, then row 2, and so on. All right, here we go. So we need a loop, we'll need a nested loop for that. So these are the rows, I. There's 100 rows. We have J. And there are how many columns? 200. And we need to, so here we're scanning across the rows. So for each row I, we're going to look at each element J, one after another, and append them to a vector. So we're building up a vector. So what do we push back there? It's the element at ij. That's what it looks like. That's an individual element in this two-dimensional array. It's the element at row I, column J. We're ranging across J right now. You can think of I as fixed in the inner loop. I is fixed, just ranging across J. So we pick off each value across that row from 0 to 199. And then once we do that, we go down to the next row. And then we do the same thing all over again. But now the function returns a vector of int, and we've constructed it here, but we need that to declare that thing. We have an empty vector v, and then we're going to push onto it. And then at the very end, we need to return it. And it's complicated to think about what code underlying machine instructions get generated by the compiler. But in an optimal scenario, perhaps we can say an optimizing compiler will only create a single vector instance. And so when we return v here, we don't make a copy to the calling code and discard the locally scoped to v here. So that's a topic that we're not going to get into. All right. Let's look at number 6. Implement a function called findMax that determines the maximum value in a two-dimensional array. The maximum value, the biggest number in a two-dimensional array. findMax. This is the declaration. There are rows, and columns, and these two things are constants. You don't have to declare them in your program, in your code. Just use them. Assume that they're already defined for you. Let's find the largest double, not an integer. Let's find the largest double inside two-dimensional array A. Well, it's going to look a lot like this. When you're working with two-dimensional arrays and you're looking for one thing, you've got to have a nested loop there. You have to scan across the rows and columns. And we're looking for the biggest value. So we're going to keep track of the biggest value. If what we're currently at, V of, I said it's I, isn't it? A, rather. A of ij, if A of ij, so we're going to look at one after another, and we're going to compare it to what we think is the biggest, what we've seen so far as the biggest. If it's bigger than our current biggest, then it's the new biggest. That's the idea. But the thing is, we didn't initialize biggest. What do you set it to? 0? What if the two-dimensional array contains only negative values? We can't start at 0. You could set it to the smallest possible negative double. You could do it like that. Anybody have a different idea?
You just said like the starting point of the array.
Yeah, use the first element in the array. Because at this point, we could say, well, this is all we've seen. So remember, when we do this comparison, we're looking, biggest represents the biggest number from all we've already looked at. So let's start by looking at one thing. And since we've looked at nothing so far, we will set the biggest to A00. Now, if the two-dimensional array contains only negative values, we start with a negative value. So we'll never, rather than mistakenly starting at 0. No.
Are you sure you want to spell double like that?
Spell what?
Double like that?
Deoble? That's okay for the quiz. Not for real life, though. Thank you. So we start at the first one, then we can just you think about the algorithm. Okay, we're going to look at each value and keep a record of what's the biggest thing we've seen so far. So we're going to look at the first one, and since we haven't seen anything yet, we set our record-keeping variable biggest to it. Now this logic works. We redundantly examine A00. So that's okay. Small price to pay. All right, number 7, I think. Search. Implement a function that searches for a given value in a vector of integers. If the value is found, the function returns the index of the value in the vector. Otherwise, it returns -1. Do not assume the values are in order. Do not use binary search. And there's an example. Let's implement search. I'm just going to be easy and do this. We got to look at every element. We're going to try, if we have to look at everything. And when we find it, we're going to return the index of where the value k is. And if we don't find k, we're going to return -1. So we're going to, when we find it, we'll find it in the loop. If we pass through the loop and we don't find it, then we're going to return -1. So all the valid indices start at 0. So -1 is what's commonly used to mean that it's not there. So we're looking at each value at in V of I. If V of I contains k, if V of I equals k, rather, we found it. So we return what? I, good. That's the index where k is, the first appearance of k. There may be multiple appearances of k in the vector. Yeah.
Shouldn't in the for loop I
less than 100, so it'll be I less than B dot size.
Oh, thank you. Yeah, that's the problem with copying code, isn't it? Thank you. Yeah, copying code is actually very dangerous in real life. I think some programmers will not copy code. That's their default position. They need to write another line of code. They don't go back and copy it. They'll write it from scratch right there, just to make sure that they're not skipping a detail like I just did. See? I have noticed that with some other programs. I'm not like that, but I do see the value in following that principle. Because when the size of the code gets a little big, you're not going to want to write each line. You're going to copy big chunks, but that's a different matter, actually. All right, so number 8, binary search. So this, we presented this last time, right? We went over this. I could just bang it out really fast because I've done this a million times. If you want to see me do it, I'll do that. But I did present pretty thoroughly about this in the last class. Do you want me to do this now, or just to repeat the exercise so you all see it again? Or do you want to skip this and move on to other topics that we haven't looked at yet? I'm not adding anything to the course. Don't worry about that. It's not like if we cover everything early, then we're just all going to take a break, and we don't need to do anything else. What do you want to do? Look at this again, or do you want to move on?
Can we look, or can you do it again?
You want to do it? Okay. I'll pretend I'm on the quiz. Okay. So binary search, you should just have this down. If you're especially a computer science major, if you're a math major, you know, you're going to have to memorize this for the test. But if you're a computer science major, computer engineering, you really need to know this very well. You should be able to just come up with this, say in a job interview. They say, hey, just write that down for us. Here's a piece of paper. Come back in an hour. Just sketch out the algorithm for binary search for me. And just testing to see if you've, if you studied well when you were in school, because you're going to need to do those kind of tasks if you're hired. So here it goes. We've got a vector v, and we need to find k in v. And so we have a start point, and we have an end point. So S and E represent those. And the end point is going to be the last valid index. You can go one past the last index, and that works as well, but the code is a little bit harder to reason about, actually. So we'll do it this way. And then we need to compute the midpoint and then check to see if k is at the midpoint. But that's done in a loop. Let's do the loop. So while, and we know that S and E are going to move towards each other until finally S passes E. And when I do this, I did this last time, so I remember that that's the inequality. Oh, I'm sorry, it's this. Or it could have been this, right? Maybe it's that. And you don't know this. I can't remember that. I remember it from Monday. Okay. But next quarter, am I going to remember that? I got to go and reason over the code again. I can't remember the algorithm exactly. But I do remember the algorithm exactly because I covered it 2 days ago. And I know that this is the condition. S must pass E for the loop to continue. Of course, there are other ways to formulate the problem where you would have a different condition. We need to calculate the midpoint. That's S plus E divided by 2. And there we get integer truncation, or truncation to an integer. And that works. We looked at that last time. And here's the point. If, and I'll do this a little differently, if k is less than v of m, that means k is small. That means we're going to bring the end, E, down to the midpoint. Well, one less than the midpoint. We already looked at the midpoint specifically. So S and E point to locations in the vector that we have not yet compared to K. If K is bigger than V of M, the value at the midpoint, that means K is big. It's going to be in the right-hand side of our division. And so we're going to want to bring the start point up, the start index, to M plus 1. Else, we found it. If K is neither less than V of M nor bigger than V of M, it must be equal to V of M. Oh, what are we going to return? It's not, let's see, int. We're not turning true or false whether we found it or not. We're returning the index where K is. What is the index where K is? Huh? Got it, everybody? Thank you. M, that's the thing we're looking at. We're looking at M. What's the value at M? So we're going to return that position. Now, let's suppose we go through the loop and we never return M, and S passes E, then we return -1. We didn't find it. And I'm not going to explain why that condition is good. I covered that last time. I don't want to get into those details. Yeah.
The condition, shouldn't it be less than E?
Oh, I always get this wrong every single quarter. And I think it's good for you. Thank you very much. S must be less than or equal to E. Thank you very much. Thank you. I was thinking this, and you could do this. Well, not, is that not? Oh no, that's not not. That's not. Well, not S greater than E. And that's what I was thinking. I didn't, I should have put it like this. S must be less than E, or it can also be equal to E. And then when we compute M, when S and E are equal, then M also equals S and E. What's the average of two numbers that are the same? That's the same number. So that means we're right there. And, you know, if this should be, if K is there, then, or if K is there, then we're going to return M. If K is not there, either one of these is going to execute, which means E will then become less than S, strictly less than S, and this will fail in the next iteration. Then we return -1. Anything else?
I have a question on your code for 6.
Number 6?
Yeah. Are you supposed to return anything?
Oh! Look at all the mistakes I'm making. We have to return the biggest for number 6. We found it, but we need to return it. Thank you. You might lose a point on the quiz for that. You wouldn't lose a lot for that, but you might lose either nothing or take a point or 2 off. Okay. Number 9. Flatten. What is it? That's a duplicate, right? We did flatten already.
The next one is 6.
Is it the same thing? It's a vector.
Yes.
It's exactly the same, isn't it? Find max. Oh, that's the same thing, right?
Yeah.
You know what it is? I forgot. I stopped at 8 somehow, and I didn't go and change 9 and 10. My mistake. That's it. Now let's take a look here where we are. We've got everything done except for this one topic on sorting. So this is another algorithm similar to binary search. You're going to need to think about this algorithm more deeply than binary search. It's a little bit more complicated, not much more complicated, just a little bit more. And then you have to memorize this and then reproduce that from memory on the final exam, not on the quiz. Sorting this will not be on the quiz on Monday, but on the final, it will be asked. 100% guaranteed, I'm going to ask you to write down the algorithm to sort a vector or an array. And here's the lab. And, you know, you can look up solutions. There's many different ways to sort values. You know, what I mean by sorting is putting something in order. If you have a vector of values and they're in increasing order, so the smaller values come first, the bigger values come later, then that's already sorted. It's in sorted order. But if you get a vector, and then, of course, the benefit of having a vector in sorted order is that you can use binary search on it, for instance, to find things very quickly. And that's one example why you would want that. But if the values are not in sorted order, and the situation that you're working in requires that they be in sorted order, then you need to sort them. You need to move them around. And this is an old problem. This is a fundamental, extremely important problem in computing. But after they first invented computers, this was top of the list. This is something that just had to get done and was done all the time. When you're data processing, you know, sorting is such a fundamental problem and so common that when you do solve data processing problems, you come to this point where, well, yeah, we got to have these things sorted. So it's not like an obscure topic. It's one of the core topics, actually. When you just after the very invention of automated computing, that sorting became an important problem. And the initial sort of theoretical research on computing was done on sorting at that time from the very beginning. So there's a lot of theory actually developed around sorting. And it turns out that you can sort sequences of values inefficiently using a simple approach, or efficiently using a more sophisticated approach. And the differences between the two kinds of sort routines are dramatic. An inefficient sort routine just simply will not terminate for large data sets. And they'll terminate in an unreasonable amount of time, you know, like days or something like that. But for if you use an efficient means, it dramatically cuts back the amount of time that's used to sort the array. Now, in this class, we're only going to look at the simple, inefficient methods for sorting, which are, you know, they're good enough for small data sets, you know, 1,000 items. They're good enough. And I recommend that when you go about this lab, that you try to do it on your own. Come up with your own, rather than just looking it up on the internet. Try to figure it out. How would you shift values around in a vector to put them in a sorted order? What is the algorithm that you're going to use? Now you'll end up using a nested loop. It'll look something like this, with a for loop within a for loop. There's no way to do it with a single loop. It's impossible. It's been theoretically researched from the very beginning of computer science. You have to have a loop within a loop. There's not a single, if you have a single loop, then that's called, that would be a linear algorithm. It would run in what's called linear time. So the amount of time taken to do the sort would be based on the number of elements that was in the vector, but that is impossible. And so you need to do, you have this sort of linear component where you're looking at each value, but then there's another sort of, in the inefficient method, there's another, for each value that you look at, you have to do something else which requires scanning through the array. But I don't really want to start that right now. We're kind of near the end of today, and I think I'll just wait. Once again, it's better, rather than having me present that to you, a solution, or having you look it up on the internet, I highly encourage you to try to solve the problem on your own. And if you come up with a solution, that's fantastic. And if you can't, and then you do some research on the internet and look something up, that's great. You could do that as well. Now, don't use merge sort or quick sort. Those are the sophisticated, efficient algorithms. You'll need to use something like insertion sort or bubble sort. And there's a bunch of, they're all named different things. The ones that look like, I don't want to get into that. So is there anything else? So this is a topic we still need to talk about, and you have to do another lab on that. And that's it for the class. We basically covered everything. Is there anything that you want me to talk about now? I want to finish. That's it, right? Okay, good. So there is a course survey. I want you to fill this out. You can start distributing that back there. And you know what to do with that when you're done, right?